Hi everyone! In this video we're going to talk about conformational analysis, but first I wanted to do a warm-up problem. Alright, so I want you to determine if these two molecules are isomers of each other, are they the same? Are they different? So determine if these two molecules are the same or different. Okay, so if you want to pause the video and try to kind of walk through each molecule, one recommendation is to name the molecules and see if you end up with the same name or different names. And then when you unpause, we'll go over it together. Okay, so let's name both of these molecules and see if we come up with the same thing. So the first one on the left, let's start by numbering our longest chain. So let's see, we have 1, 2, 3. If we go down, we'd only have 4 carbons, but if we keep going right, we have 5 carbons. So that's our longest chain. And then it looks like we have a methyl substituent on carbon 3. And let's see, if we numbered from right to left instead of left to right, that methyl group would still be on carbon 3. So let's actually do that just for visualization. So 1, 2, 3, 4, 5. So the methyl group is always on carbon 3, so again, it doesn't matter which way we number it. So the name of this compound is 3-methyl. And then what prefix do we use if we have 5 carbons? Pent. So it would be pent. And then we have only single bonds, no double bonds or triple bonds. So the ending would be ANE. So 3-methylpentane. Okay, so let's do the same thing for the second molecule. Let's number the longest carbon chain. So we have, let's see, I'll start from the right. 1, 2, 3. And if I go down, I have only 4 carbons. But if I go up, I have 5. Okay, so I have 5 carbons. And then I have a methyl group on carbon 3 again. And again, it doesn't matter which way I number this. 1, 2, 3, 4, 5. Methyl is still on carbon 3. So this is also 3-methylpentane. Okay, so why did I draw these two molecules differently? Well, simply because I can. Molecules with sigma bonds can rotate their bonds really easily. But remember, if you have a double bond or a triple bond, then the molecule is essentially stuck in place unless you put energy into it and change the molecule. So if you have all single bonds or all sigma bonds, the molecule can just freely rotate, so those bonds can stick up or down or, rotate whichever way they want. So just make a note of that. Sigma bonds can rotate freely in space. And that's going to be important for our next conversation. So let's talk a little bit more about conformational analysis. So again, sigma bonds are assumed to rotate freely at room temperature. And one example is the molecule ethane. So let's draw a side view of the molecule ethane. So remember, F tells us that we have 2 carbons, and ane, the ending, tells us that we have all single bonds. All right, so I'm going to draw hydrogens, and I'm going to show the wedge and dash to indicate that there is a tetrahedral configuration around that carbon. And then I'm going to do the same thing on the other carbon. All right. Now, again, remember, sigma bonds can rotate whichever way they want. So we could rotate these hydrogens around. So for instance, if we kind of twist the carbon on the end, we would end up with the wedge and the dash up at the top, and then the hydrogen that's in the plane would be on the bottom. And we could keep twisting this any way we really want, but again, just remember that these can freely rotate. Okay, so there is another way to draw this molecule, and that's with something called a Newman projection. So we're going to draw a Newman projection for ethane up above. And Newman projections are a little strange looking. Basically, what we do is we take one carbon, and I'm going to highlight that in red. So I'm going to highlight this carbon here on the left in red. And we're going to look at this from the side or from the front, whichever way you want to think about it. So we're going to look at it kind of through that carbon-carbon bond. And I just drew a little eyeball here. That's supposed to be an eyeball. It's kind of doesn't really look like an eyeball, but that's okay. All right, so if we're looking at this from the side or the edge, oh, and actually let me use a red pen here so we can keep track of which carbon we're referring to. We're going to draw the hydrogens on that carbon. And let me highlight which hydrogen is which. So the hydrogen below carbon up above is again below carbon down below. And then the 2 hydrogens up above that carbon are up above. Okay. So now we need to represent the back carbon. So I'm going to highlight that in green. Hopefully you're not red-green colorblind. I know some people are. I should probably have more color options. But the back carbon is going to be represented by a circle. So that's actually behind these bonds here. So let me just draw over that. And we're also going to draw its hydrogens. So there's one up above, there's one off down below to the right, and there's one kind of back behind that carbon. And so I'll highlight those as well. So let's see, what colors can I use? Let's use purple for the hydrogen up above on that back carbon. And we'll use, oh boy, Maybe we'll use green again for these bottom hydrogens. I wish I had more colors. Okay, so hopefully you can kind of visualize what's going on. I'll also post another video using a modeling kit so that you can see what I'm kind of doing here. So I'm really taking the molecule and turning it so that I'm looking at it straight down that carbon-carbon bond. And then I'm trying to figure out where the hydrogens are in relation to those carbons. Okay, so this is what's called a staggered conformation. Oh, I spelled that wrong. Staggered. Staggered conformation. So all of the hydrogens are staggered, so they're not all lined up together. They're actually offset from each other. And they're actually offset by 60 degrees. So if this front blue hydrogen is compared to the back purple hydrogen, those are 60 degrees apart. So what if we rotate one of the carbons 60 degrees? Well, we would end up with there we go. We would end up with hydrogens that are kind of stacked on top of each other. If we're looking down that carbon-carbon bond. Try to draw this as best as I can. And then let me also highlight the hydrogens so we can keep track of which one is which and how we turned these. Let's see, so purple's in the back, and then we've got our yellow hydrogen that has shifted over 60 degrees, and then our green hydrogen stayed in place. Okay. So this doesn't look exactly like the first picture, but basically the green hydrogen stayed where they are, the purple hydrogen stayed where it is. We just rotated the front carbon. So we rotated the blue hydrogens and the yellow hydrogen 60 degrees. So now every hydrogen is lined up with the back hydrogens. And this is what's called an eclipsed conformation. Okay. So, which one of these conformations do you think is more stable? Do you think it's more stable to have staggered hydrogens or eclipsed hydrogens? Staggered, because remember, electron groups want to be as far apart as possible. So if we can spread out the hydrogens so that they're not overlapping each other, then that is ideal. So the staggered conformation is more stable. And then the eclipsed conformation is less stable. It's still possible to have eclipsed hydrogens, but most of the time this molecule would prefer to have staggered conformations because there's less energy involved. So let's actually look at the energy diagram for these Newman projections. All right, so this is specifically for ethane. So let's draw some x and y axes. And energy is on the y-axis. And then we'll just put rotation on the x-axis. So initially, we started with a staggered Newman projection, which is pretty low in energy. It's pretty stable. And then the eclipsed conformation is pretty high in energy. It's not very stable, so we'll draw that way up here. Now, we could rotate our carbon another 60 degrees. So let's go back. So if we rotated our carbon another 60 degrees, this hydrogen would move here, this hydrogen would move here, this hydrogen would move here, and we'd end up with another staggered conformation. So we could keep rotating the carbon and go back and forth between eclipsed and staggered, eclipsed and staggered. So on this diagram, if we did that again, so if we rotated it, we'd have another staggered conformation, which would be low in energy. So our diagram actually starts to kind of look like a sine or cosine wave, where we're going up and down between staggered and eclipsed. Okay, now what if we don't have all hydrogens? What if we have a different group bonded to carbon? How does that affect the energy of the molecule? So let's look at another example. We'll look at butane. So butane has how many carbons? 4. Okay, so normally we would draw butane like that, right? At least in the bond line form. But what we're going to do is really just focus on the 2 central carbons. So let's draw what that would look like from the side. And I'll draw this in the staggered conformation. So let's say we have a methyl group up above. So that's this carbon up here. And then we'll draw a methyl group down below on the other carbon. So that's down here. And then remember that the 2 middle carbons have 2 hydrogens attached. So they're CH2 groups. So let's draw those, but remember both carbons have a total of 4 bonds, so they are tetrahedral. So we should draw the wedges and the dashes. Sometimes I switch my wedges and dashes, but whatever works for you visually is fine. Okay, so let's draw that eyeball, that kind of creepy eyeball, and we'll show it looking down that carbon-carbon bond, and then we'll draw the Newman projection. So I would actually like you to try drawing the Newman projection for this molecule. So pause the video, and when you unpause, we'll go over it together and see if we got the same thing. Okay. So let's draw our Newman projection down below. All right, so let's draw our front carbon. So that will be red. And you don't have to draw these in different colors if you can visualize it. That's totally fine. This is going to be a little easier because we have methyl groups instead of hydrogens. So it'll be a little bit easier to kind of tell what's going on. So on that front carbon, we have a methyl group down below. We have a hydrogen kind of going back, and then we have a hydrogen coming forward. So the hydrogen on the left is our dashed hydrogen. The hydrogen on the right is our wedge hydrogen. And again, I'll make another video showing a molecular modeling kit version of this so you can visualize it a little bit better. Organic chemistry is tough if you have trouble visualizing, and I completely understand the struggle. Okay, so now let's draw our back carbon, and that will be, let's do purple. Oops. Oh, I don't have purple. We'll do that in blue. Okay. All right, so that's our back carbon. It's represented as a circle, so it kind of looks like a steering wheel almost. And on that carbon, we have a methyl group up above, and then a hydrogen kind of coming out. So that's our wedge hydrogen, and then a hydrogen going back. That's our dashed hydrogen. Okay, so hopefully you got the same thing I did. If not, just make any necessary corrections, and let's see what happens if we do a 60-degree turn. And of course, we can always go back and forth between these different conformations because we can very easily rotate the carbons and their bonds. So I draw the double-headed arrow to indicate that we can go back and forth. All right, so let's do a 60-degree turn. So we're going to take this back methyl group and shift it over 60 degrees. Okay, so we'll keep our front carbon the same. So we have two hydrogens up above and then a methyl group down below. And then with our back carbon, the methyl group has now shifted 60 degrees. And then the hydrogens down below have also shifted 60 degrees. It's kind of hard to draw, but all right. So our first conformation was a staggered conformation, right? And the second conformation is an eclipsed conformation. So let's keep going. Let's do another 60-degree turn. So again, we're going to move this methyl group 60 degrees. All right, so the front carbon and its bonds stay the same. But the back carbon is what rotates. So now that methyl group is down and to the right. And then the hydrogens are also moving, so they're kind of off to the bottom left and the top. Okay, so let's keep going. Let's go another 60 degrees. So we're going to take that same methyl group, rotate it 60 degrees. Oh, let's see if I can squeeze this in here. So our front carbon stays the same. Oh, my pen likes to go bold towards the bottom of my iPad. I'm not sure why. So now we have actually our back CH3 group behind, and then the hydrogens are also lined up with the front carbon's hydrogens. All right, so that's another eclipsed conformation. Now let's do another 60-degree turn. So we're going to move our methyl group again on the back carbon. Okay, so this structure looks pretty similar to the third structure we drew, where the methyl groups are kind of offset from each other, so they're 60 degrees apart. It's just flipped, right? So that's kind of similar. Okay, and let's do one more 60-degree turn. And we have another eclipsed conformation. And this one looks very similar to the second figure we drew. So the methyl group is kind of right behind a hydrogen. And then if we did another 60-degree turn, we just end up with our original structure. Okay, so we have 6 total structures here, or Newman projections. So let's try to rank these in terms of the most stable conformation and the least stable conformation. So we already saw that the staggered conformation is the most stable conformation. However, here we have a few different staggered conformations. We have our first one where the methyl groups are directly opposite each other. And then we have 2 staggered conformations where the methyl groups are closer. So one interesting thing is if you do have methyl groups kind of 60 degrees apart from each other, or really any group, like if you had chlorines or bromines there, if they're 60 degrees apart, that's not very stable because we have these pretty large electron groups that are getting really close together. And that's what's called a gauche interaction. And so that's also present in this staggered conformation down below. Those methyl groups are 60 degrees apart, and they're a little too close to each other for comfort. They would rather be further apart. So looking at all of our staggered conformations, the first one is the most stable because the methyl groups are really far apart. So let's label that as number 1. That's the most stable. And then the other 2 staggered conformations are pretty similar to each other. So those have equal energy, but they're less stable than our first staggered conformation. So we'll label those both as 2. Okay, so now let's keep ranking our structures in terms of energy. So let's look at all of our eclipsed conformations. We know that they're all less stable than the staggered conformations, but which one is the least stable? Probably the one where the methyl groups are directly lined up, right? So I'm going to label this structure number 4. So that's going to be our least stable conformation because those methyl groups are lined up perfectly, and that's going to cause a lot of instability. Those electron groups would prefer to be further apart. So now if we look at our 2 other structures, our eclipse structures, the methyl groups are 120 degrees apart, so that's a little more stable. However, those methyl groups are perfectly lined up with hydrogens, which is not very stable. So those 2 are still less stable than our staggered conformations. So we're going to label these 3. And I'm giving them the same energy because they're pretty similar. They're just rotated differently. Okay, so we have our most stable structure and our least stable structure. And there's actually a couple of other terms that we use to describe our most stable and least stable structures. So number 1, we say that the groups are staggered anti-periplanar. Let's see if I can fit this in here. Periplanar. Actually, let me just write it down below, and that'll be easier. Okay, so that tells us that the two methyl groups are opposite each other. It's just a fancy word for that. Okay, and then the least stable structure, we call that eclipsed syn-periplanar. All right, so anti means that the groups are as far apart as possible. Syn means that the groups are lined up perfectly with each other. So those methyl groups. Okay, so let's actually draw the energy diagram for butane and all of its different Newman projections. So I'm going to draw the same x and y axes that we did before. So the y-axis is our energy level. The x-axis we're just going to call rotation. Okay, so we said that figure 1, or our first Newman projection, was the most stable, so it would have really low energy. And then, if we go back, we rotated that 60 degrees and ended up with our second structure, which we gave the energy level 3. So that was the second least stable. So let's give it an energy up here, for instance. All right, and then if we go back, we did another, oops. Oh, it won't let me go back. Ah, I went too far. Okay, so the next structure, we gave an energy level of 2. So this was the second most stable structure. So we'll put that kind of in between 1 and 3. And then the next structure we said was the least stable structure. Okay, so that was labeled number 4. So that's going to have the highest energy because it's the least stable structure. So we'll put that way up above. All right, and then we rotated this again and we ended up with our second most stable structure again. So that was number 2. So we'll put that next. And then we ended up with another level 3 structure. And we could keep going, so we could also go back to 1 at the very end. So if we put this all together, kind of looks like a roller coaster. All right. So actually, we can measure the energy difference between all of these structures. And what we find is that the difference in energy between level 1 and level 3 is 3.6 kilocalories per mole. And then the difference between energy level 4 and level 1 is 6.0 kilocalories per mole. Now, compounds can freely rotate if the energy barrier is less than 20 kilocalories per mole. So I'll write that up above. Okay, so compounds can freely rotate if the energy barrier is less than 20 kilocalories per mole. So even though butane does have some less stable Newman projections or structures, it can still freely rotate because the energy between the least stable and most stable structures is only 6 kilocalories per mole. So that still works. Now, this is at room temperature. If we were to cool down the molecule, then butane would prefer to be in one of the more stable structures. So at lower temperatures, we have less energy, so they would like to be more stable. But if you're at room temperature, this rotation can freely occur. Okay, so I have a couple of skill builder exercises listed here that might be useful. Skill Builder 4.7 on page 151 will help you get practice with Newman projections. And then Skill Builder 4.8 on page 156 will get you even more practice with thinking about eclipsed versus staggered and the energy levels and the relative stabilities. So definitely work on those because this is something entirely new that we're learning. And again, I'm going to put together another video showing you ethane and butane and how they can rotate with a molecular modeling kit so you can actually see in 3D what's going on. So I will see you then.